Okay, so let's talk about this. Chapter 22 is dealing with patterns of electric and magnetic fields in space. And so we've been focusing a lot at electric and magnetic fields at particular observation locations and looking at charges at those observation locations and seeing how those fields affect those individual charges. We're going to be taking sort of a more global picture now, looking at patterns, overall patterns in space of electric magnetic fields, and then using some ideas from geometry to lead to different relationships between field and charge. And I'm going to start with a little demo here. What I have here is a box, okay? Just a rectangular shaped box. And on the outside surface of the box, I am calculating or measuring, I should say, the electric field on various observation locations on the surface. And we see it's all kind of everywhere I've put an electric field vector, it's kind of pointing away from the interior of the box. So here's a question. What's in the box? And the options are, if I can get this thing from freaking out here, the options are net positive charge, net negative charge, net charge of 0, or there's just not enough information to figure out what's inside the box. Question, yes. Let's come back to that question. That's a good question. Okay, so someone's asking a question about what if you had a negatively charged ring and you put a box at the center, what would the pattern of field around the box look like, right? And so we'll come back to that. That's a good one. We say that most of us will say that there is positive charge inside the box. How do you know that? It's pointing away from the interior, right? We know that electric fields due to positive charges point away from positive charges. So if I were to zoom in here, and I got to click it. Oh, there it is. So there's our positive charges. Okay, these red of course is positive. The way the book color conventions used in the book, red's positive. So we say, okay, positive charge inside the box, creating this electric field. The box is not. The box is neutral. The box is not. Box is just imaginary. It doesn't even have to be a real object. It's just sort of a mathematical box that we're just kind of using to hide the charges. Let's try another one. Let's say, how do I do this? Here we go. Let's look at this one. And here I am drawing electric field vectors again at observation locations on the surface of the box. I'm changing our convention a little bit. I'm putting the tips of the arrows rather than the tails at the observation locations just so we can see these arrows and they're not inside the box. What's inside the box? Same question. It's got to be negative charge, right? Because it's pointing into the box, okay? Electric fields point towards negative charges, okay? So if we zoom in here, of course, negative charges are blue in the color conventions used in the book. So, let me zoom in a little bit more. There's our negative charges. Okay, so far so good. Let's try another one. What's inside the box? Here we have some electric field pointing one way, some electric field pointing the other way. And on one side, kind of perpendicular to that surface, kind of parallel to the lateral surfaces, and then pointing the opposite way on the other side. What's inside the box? Oh, a bit more disagreement this time. Some of us are saying that there is net positive charge inside, some net charge of 0, some not enough information. Those of you said positive. Why positive? It's going away, okay? There is this tendency on both sides that the electric field is kind of pointing away from the interior. It's a little stranger than what we saw before, right? Because the fields are all parallel on one side or the other. But we have seen something make a pattern of field like this before. What could this possibly be? Dipole, let's see, a dipole, let's try a dipole. We have negative on that side, positive over here, and here the electric field is pointing that way, right? But over here the electric field is pointing same direction, right? So that's not quite a dipole. Any other thoughts? The magnitude of those vectors look pretty much the same, right? And the directions, at least on either side, look the same. So we're getting, on one side or the other, a uniform, mostly uniform electric field. Where have we seen uniform electric field before? Okay, wire, like a thin rod of charge. Well, a thin rod of charge will make a uniform field in magnitude if it's long enough, but of course it's going to spread around, right? It's going to be out here, it's going to be pointing out towards us, and then it's going to be pointing down over here, and then it's going to be pointing in on the backside. So it's going to have that radial pattern to it. Someone else said something else. Capacitor. Okay, where is the box in relationship to the capacitor, I guess is the question. Because, okay, so let's look at a capacitor field. We have a capacitor is, say, positive charge here, negative charge here. Inside the field points what direction? Inside the capacitor, the field's going to be pointing what direction? That way. All right. Outside, what's the fringe field look like? It's pointing the other way here, and the fringe field magnitude is smaller, right? So we get a small fringe field here. So, I don't know, not quite what we want, right? Because it's the same magnitude either side. But what makes up the capacitor? Two plates, right? What would the field of one plate look like? One positively charged plate. On this side, we get a electric field pointing. Yeah, it's pointing away like that, right? On this side, the field points to that way. The other side, the field points the other way. And given the same distance away, the magnitudes of those fields should be the same, right? So maybe we are cutting through the interior of the box. I didn't tell you that there couldn't be charge outside the box. Okay? But we do have charge on the inside. It's cutting through one portion of this positively charged plate. Question? Someone had a question. You okay? You okay? So there is charge inside. There happens to be charge outside as well, but there is charge inside, and because there's charge inside, we still get this field or pattern of field where it's mostly pointing towards the exterior of the box, right? Pointing away from the center of the box. What about this one? Okay, so here we have electric field kind of pointing inward on this side, outward on this side, and parallel to the surface of the box, just about on every other surface. What is inside in this case? Okay, so we have a majority vote for a net charge of 0. This pattern of field looks like what? What did we just draw here? Dipole. Well, okay, well, let's see. Does it look like a dipole? The dipole, let's look at the dipole again. Now, it's true a dipole would have a net charge of 0. Let's see. Well, let's draw it the other way. We'd have a negative charge here, positive charge here. That field points that way. That field points that way at that observation location. But what if I'm at this observation location? What's the direction of the electric field there? Yeah, the other direction, isn't it? So it's not quite what we want, right? Because it's the same direction everywhere. This could be the capacitor, right? Where's the box in relationship to the capacitor? It's inside the capacitor gap, right? So if we chose this as our box, this would produce this pattern of field, right? And again, if I click here, Didn't say I couldn't have charge outside the box. Once again, there's got to be some charge somewhere that's producing this electric field. But apparently we are inside the capacitor gap, and so the box is actually surrounding nothing at all. Okay, and we have positive plate over here, negative plate over here, producing a uniform electric field. I'm not showing the entire plate. Producing a uniform electric field pointing to the right. Okay, so what's the basic idea? The basic idea is that we want to relate these various patterns of electric field in space around a closed surface. We're just using a box here. Try to relate this to the amount of charge inside this closed surface. Okay, so somehow the electric field pattern on a box, or just any closed surface we'll see, somehow tells us something about the charge inside. Okay, if we get the field mostly pointing toward the outside, we know there's positive charge in that box. If we have the field mostly pointing toward the interior, we know there's negative charge pointing, or negative charge inside that box. If we have kind of a mix of both, we have sort of equal amounts in some sense of field pointing in and field pointing out, and somewhere else it's just kind of parallel to the surface, we had a charge of 0 inside that box. So we can kind of see this qualitatively. What we want to do now is make this quantitative.